Welcome to Lecture 8. We're going to continue here with Unit 3, and we're going to push into winter weather forecasting and really get into the heart of precip types. And then when we move into Lecture 9, we'll get into snow ratios. All right, so what are some of the challenges about forecasting winter weather? Well, there's lots of them. And, it's hard to really rate what's the hardest, but I would argue winter weather, especially when you get into the micro scale stuff like lake effect snow, is definitely some of the hardest and most challenging things to forecast. All right, so you got to ask yourself, first, what is the precip type? Are we going to have rain, freezing rain, sleet, snow? If you can't get that right, then you're going to get everything else wrong, obviously, right? You have high impacts on a minor forecast error. So let's say it's the summertime and you forecast 90 and it's 92. Not really a big deal. But what about in the wintertime when you're thinking it's 33 and it ends up being 31 or 30? Now it becomes a big deal. So you have a high impact on minor errors, right? And this is what makes it very challenging. A degree or two could be a huge difference between snow, sleet, freezing rain, or rain, all right? QPF errors are much more noticeable. So again, in the summertime, let's say you go for a half inch of rain and you get an inch of rain. Well, yeah, maybe some people might give you some crap for it, but for the most part, probably not that big of a deal. But what about with winter weather? Let's say you're going with a quarter inch of QPF and you get 3/4 of an inch of QPF. Now you have a problem, especially with your snow forecast or ice or sleet. All right, so when you're off on winter weather, it's really noticeable, all right? And you need to consider the vertical temperature profile, not just the surface temperature. A lot of people think, oh, well, it's below 32 at the surface, we're definitely going to get snow. And I'm going to show you that it's really not that simple. It's a lot more detailed and there's a lot more different concepts involved in it. So why are winter weather forecasting skills critical in regions where frozen precipitation is rare? Look at somewhere like where I live in Starkville, Mississippi. We don't get a lot of snow. I've actually seen 8 inches of snow here. I've seen a few winters where we got 3 or 4 snows. But in general, we're getting a snow maybe once a year. So if I blow a winter weather forecast down here, I don't get a chance to redeem myself for maybe a year. Whereas if I live in Buffalo or further north, Minnesota, Wisconsin, places like that, you blow a forecast and hopefully probably a week later you get to redeem yourself, all right? So you have more opportunities to redeem yourself, and if you do miss one or two, you can fix that by, again, redeeming yourself later on. Down here in the South, it's not really that way. Plus, down here in the South, if you say the S word, if you say snow, you're going to almost incite panic. And everyone's going to go to the store and buy all the milk and bread, which, to be real with you, I never really understood that because to me it would be more chips and beer, but hey, that's just me. But regardless, if you say the S word, if you say snow, you're going to incite panic down here, all right? And look, I'll be the first to say I'm kind of a wimp to the cold, and I love snow and all that. And I did live in D.C. for a long time, so I'm kind of used to driving the snow. And I know the South gets a bad rap for the cold and the snow. But in fairness, in the summertime when it's 90, 95 degrees up north and everyone up there is suffering, that's just a normal day down here in the South in the summer. So it's all about region. It's all relative to where you grew up. So just keep that in mind. But this is why I really focus on it in my classes here, both DL and on campus. Obviously, on campus here at Mississippi State, we have a lot of people from the South. I try to make it, really ingrain into them that if you blow it, you're probably going to hear about it for a long time. So here's some winter weather definitions. Hopefully you know what snow is. I've actually had some students who have never seen snow. Maybe if you grew up in South Florida or Southern California or places like that, you haven't seen it. You got freezing rain, you got sleet. In Canada, they're referred to more as ice pellets, and then of course you have rain. So let's break these down. You can read the definition. Hopefully you've all seen snow. What's really beautiful about snow is no two flakes, no two crystals are the same. And I've seen these books that are just amazing, showing you all the different types of snow crystals, and it's just incredible. It's really beautiful. You got different types of snow. You got more icy snow. You got more fluffy snow. You got more dense snow. You got this snow that I call stinging snow, where it hits you in the face and it doesn't feel the best. Sometimes you get really like fat flakes and small flakes. So they all come in different shapes and sizes. So here's a good picture of some snow. I think this is this is from my good friend Doug, and this is from, I think, the National Weather Service in Buffalo. Look at this. This is up in the Great Lakes and up in the lake effect belt there. I think this is near Oswego County. You can get snow so deep that if you don't go on the roof and clear it, it will cause enough weight on your roof to cause the roof to collapse. One of the greatest snowstorms in Washington, D.C. history, the 1922 Knickerbocker storm, there was it was a heavy wet snow. It was about 30 inches of snow, and it caused the roof of that theater to collapse and it killed over 100 people. So it can be dangerous, and there are times in some of these belts you have to get up on your roof and clear the snow. Sleet, sometimes referred to as ice pellets, again, especially in Canada, you'll hear that. But in the United States, you'll hear a lot of people often define this as frozen raindrops. That is not correct. There are some circumstances where that can happen. It's fairly rare, and I'm going to show you that. But what is sleet? Sleet is a partially melted snowflake that refreezes before reaching the ground, all right? So you have an ice crystal. You have your snowflake. As it falls through a melting layer, as long as that ice crystal survives and then falls back through a sub-freezing layer where it gets cold enough to refreeze, you can get sleet. If you lose that ice crystal, if you have a total melt, then no more sleet, all right, unless you get these weird circumstances. I'll show you a couple. But let's just keep it simple. If you lose that ice crystal, you're not going to get sleet, and you're looking at either freezing rain or rain. All right, and they can range in appearance from clear to milky white depending on the amount of freezing or melting, I should say. So if it just melted a little bit, it'd be more milky white, and if it melted a lot, then it would be more clear looking. I love the sound of sleet. Sleet actually is awesome, especially on a tin roof. It's really cool. Hopefully you've experienced that before. It does make for treacherous driving, but sleet is so much easier to drive in than freezing rain. That is by far the most dangerous. And of all the hurricanes I've been in and all the snowstorms I've been in, the most dangerous and most scared I've ever been was driving in an ice storm in St. Louis. All right, so freezing rain is no joke. And sleet can be dangerous as well, but freezing rain, which is what we're moving into here, is what's really, really dangerous. All right, this is when the rain freezes on contact with roads, power lines, cars, windshields, you name it. And it's super cold, so it already has a temperature below freezing. So when it hits that sub-freezing layer and makes contact with your car or the ground or the trees, then it will freeze. All right, maybe the result of total melting of the snow. Or a cloud with a minimum temperature that is not cold enough for ice crystal formation. We're going to talk about this, but you got to get down to minus 10 degrees Celsius in order to get ice crystals to form. That's a good baseline temperature, all right? So you could be below freezing the whole profile, but if you're not getting to minus 10 and if you don't have moisture within that minus 10 area, you will get freezing drizzle, all right? And we'll talk about that in a lot more detail, all right? So obviously, it's actually very beautiful if you've been in ice storms, but it's very destructive. I mean, you see these pictures here, bringing down power lines and trees and making travel almost impossible. Trees splitting in half. I mean, I've been in some bad ice storms where you can hear the trees and branches breaking in the forest. It's pretty crazy. Look at that. A transformer came down. I believe that's from that bad ice storm in the late 90s in Toronto. So, right around that area in Ontario. It was a really, really bad ice storm. Okay? Look at that. Try to get your mail on that. Not going to happen. So here's probably what we all grew up with. I know I had a USA Today weather book, and this kind of shows you the breakdown between rain and freezing rain and sleet and snow. And this is just a way oversimplification, all right? But this is probably what we most grew up with and most kind of understood. But we're going to break it down in more detail. And then also here's just a little oversimplification as well. It's not horrible here. It does show you the partially melted snowflakes that refreeze with that deep cold layer. But it's not giving you the specifics. And we're going to talk about all those specifics here pretty shortly. All right, so two important concepts. Raindrops do not readily freeze in the air to form sleet unless there's nuclei, partially melted snowflake inside. All right, so you got to still have that crystal. And think about it. You need a nuclei aloft in order to get these ice crystals, in order to get, the super cool water to connect to that. All right, snowflakes do not begin to form in the cloud when the temperature drops below 0 degrees Celsius. People think that. People think it's colder than 0 degrees Celsius, snow forms. That's not true. In general, you need to get to minus 10 degrees Celsius. All right, we're going to break this down more and show you that it's a little bit more complex than that. But a good rule of thumb is minus 10 degrees Celsius, all right? The nuclei that ice crystals grow upon do not typically activate until approximately minus 10 degrees Celsius. That is a huge, very important concept, and that's something you're going to really need to focus on, not only with the quiz or with actual the practice portion of this, but just in general. This is a number you really got to remember. Okay. So, what are the two traditional rule of thumb used by forecasters to predict snow versus rain? Well, you have the 0 degree isotherm at 850. You would see a lot of people use that. That's better than the 540 line, but that is still not very good. Why? Well, yeah, it's telling you it's cold enough at 850, but what's going on at 925? What's going on at 700? It just leaves a lot of the details out. This is the one you hear a lot about, the old 540 line. I'm being nice and calling it a very broad first guess, but the 540 line is absolutely horrendous. All right, it is really bad. Thicknesses do not pick out the details. Yes, it tells you that the profile between 1,000 millibars and 500 millibars is below freezing, right? But it's not telling you the details within it. You could have pockets that are really, really cold, and then you could have some pockets that are fairly warm. It's just telling you what the average profile is. It's not telling you the details between 1,000 and 500 millibars. That's why you need to look at the forecast sounding. That's going to give you the details, and that's why we use BuffKit in order to break down that forecast sounding and really look at it in detail and see the pockets of warm and cold. This is just a way oversimplification, all right? Now, look, if you're Ginger Z or someone that's doing the national news and you don't have time to look at every single area, fine, all right? Maybe 540 will give you a good broad guess. But if you're at any market, whether it's the north, south, west, east, doesn't matter, you need to look at the forecast sounding. There's really no excuse to look at the 540 line. To be honest with you, I wish they would ban that from all Intro to Met textbooks, but it's there, so that's why I'm talking about it. And that's why I'm going to talk about a little bit with the thicknesses, because you'll still see people refer to that. But I'm going to teach you why. I won't go as far as worthless, but it's pretty close to it, and we're going to break down ways that you can really improve on it. All right, here we go. Got stuck there. So wire thickness values used to forecast precip type. It goes back to the hypsometric equation. But there's really big limitations with this. And again, we'll break this down in a lot of detail. All right, so obviously this is not a skew T. You don't see it skewed. This is just an easy way to visually see this. All right, so let's just pretend. All right, let's pretend you had 3 different temperature profiles, right? Let's say we had one that was isothermal at 0 degrees, right? And aloft, way up high, it was minus 10. You're making crystals, all right? So if it was isothermal at 0 degrees, if it was just straight up and down here, you would be looking at snow with a profile average of 0 degrees Celsius, right? Well, let's pretend now you had one that was going from like 10 degrees Celsius back to negative 10 degrees Celsius, right? And you had this type of profile going like this, right? From minus 10C to positive 10C. Well, is that going to give you the same as up and down? No. Up and down is going to give you the snow, where this, you're going from cold to warm, you're looking at a rain profile. But that average would still be 0. So you kind of get what I'm talking about here. Now let's flip it around. Let's say it was minus 10 and it was 10. Well, if it gets to 10 Celsius, that's a total melt. But regardless, if it's a total melt and it's minus 10 on the surface, you're looking at freezing rain in this scenario here, right? So what would this average be? Also 0, right? So this average is 0, this average is 0, this average is 0, but it gives you 3 different precip types. So you see what I'm getting at. Yes, the average may be 0 or below, but it's not telling you the details. All right, so I'm putting this up there. I'm not even going to read it. It's just there for you to have, because you might read this in discussions or see this around. There's still some people that use thickness values. So again, it's there for you to use, to have for reference. When I say use, just have for reference in case you see it, so you understand what they're talking about. But don't use this. Always use the profile. Always look at the forecast sounding, or real soundings even better. All right, so it's all there. You can look at it. I'm not going to test you on any of that, all right? But it's just there for you to have for reference, okay? All right, and then quickly, you'll see these, different spaghetti plots and different things like this. This is a Bolivius looking at the 540 line here. Now, look, if you're up in Minnesota, you're good to go, right? If you're down here in South Florida, you're not getting snow. But what if you're, in this, what if you're in Louisville? What if you're in, places in southern Illinois or, southeastern Missouri? Are you just going to rely on this, or are you going to look at the profile? You're going to want to look at the profile. All right, so thickness values can be somewhat useful, and I say that very reluctantly, I guess, all right, but they should not replace an evaluation of our hourly forecast sounding. Always look at the sounding, and this is why we're using BuffKit. All right, so let's break this down in more detail. That was just kind of a broad overview. Let's kind of dive into more of the details here. All right, so we're going to do a top-down approach on this. We're going to look at up in the snow growth region, and we're going to work our way down to the surface. All right, so sounding considerations. Is any part of the cloud cold enough for ice crystal formation? What is that magic number we talked about? -10. All right. Is any portion of the sounding warmer than 0 degrees Celsius? Do we have a melting layer? And not only does it get above 0 degrees Celsius, how thick is that melting layer? So it's not just the temperature, it's the thickness of that melting layer as well. All right. So how warm is the melting layer? Also, how deep or thick is that melting layer? All right. We're going to break all this down. Where is the melting layer found? That's important. Is that at the surface or is it aloft? I'm going to show you there's a big difference when the melting layer is at the surface versus aloft. How cold is the air in the layer below the melting layer? So let's say you had a melting layer aloft, but you have a sub-freezing layer below it. How cold is that air below it? That's important with sleet forecasting, all right? And we're going to talk about that. And also, that's really important for what else? Freezing rain. How deep is that layer of sub-freezing air, and how cold is it as well? So we're going to break all that down as well. So heterogeneous nucleation is the process by which ice crystals form from liquid water molecules as the molecules collect and freeze into foreign particles such as dust, clay, and aerosols. All right. So there's all different types of nuclei. So when they collect, they form. And then if it's -10 or colder, you start getting ice crystal formation, all right? So this is most likely at temperatures colder than -10. But it's not that simple, all right? It's really likely for sure by -12, all right? Your prime snow growth region is -12 degrees Celsius to -18 degrees Celsius. That's your prime snow growth region. But really, the snow growth region starts more at, from all my experience and all my practice and just looking through research and doing this for 20 years now, -10 is a pretty safe number. But sometimes, depending on the nuclei, ice crystals can form as warm as -5 degrees Celsius. We don't have the capability. I mean, we have some idea, but we don't know for sure the exact nuclei that's being formed, all right, or present. It's not like I can look at snowflake and be like, that's a dust nuclei, or that's a salt nuclei, or whatever, right? Yeah, we have a general idea, but we can't really break it down to that detail. Maybe someday that will happen, but as of now, we don't have that capability. So depending on the nuclei, they can form as warm as -5. For sure, about -12 to -15, you're really safe. But in this class, and for the purpose of really having a baseline and having a good starting point, we're using -10 degrees Celsius as when ice crystals start to form. All right, and this is from the Common module, and there's all different types of papers out on it as well. -10 is a pretty good safe bet. If you want to be extra cautious, you could do -12. But again, sometimes they can form as warm as -5. It does happen, but -10 is safe, and that's what we're using for this class. Wow, that was a big, if you can hear it, that was big time thunder right there. We got a thunderstorm going on outside right now. All right, kind of actually almost startled me there for a second. All right, so key points. The formation of snowflakes does not begin as soon as the temperature drops below 0 degrees Celsius. Clouds are entirely below freezing, no melting layer, may not contain ice crystals if the coldest temperature in the cloud is not colder than approximately -10 degrees Celsius. So again, you could be below 0, you could be colder than 0 degrees Celsius, but if you don't get to -10 and you don't have moisture at -10, you're not forming ice crystals. You're not going to get snow. All right. Colder temperatures increase the likelihood of ice crystal formation, but there isn't a consistent threshold temperature that triggers ice crystal formation. Again, last time I'll say this, it can form as warm as -5, maybe sometimes as cold as -15, but -10 is a pretty safe bet, and it's what I've been using the last 15, 20 years, and it's worked really well. Characteristics of the melting layer. All right, so let's break down this melting layer. All right, so this is with an elevated melting layer. How warm is the layer of warm air? All right. If the Tmax is less than 1 degree Celsius, minimal melting occurs and the snow will usually refreeze and retain the appearance of a snowflake. All right. You got to be careful with the forecast sign. What do I mean by that? Well, let's say it's zero point 0.8 degrees Celsius, right? And you feel confident, all right, this isn't going to get into that partial melt zone. We're still just got a little bit of melting. But you got to be careful because what have I told you before with Buffkit? Buffkit's not a model. Buffkit's interpreting the model data. So if you're looking at the GFS model data or the NAM model data, you better be confident that the data you're looking at is correct, all right? But assuming that it is correct, if it's less than 1 degree Celsius, minimal melting will occur and the snowflake will typically refreeze and still appear like a snowflake. I call this stinging snow. Yeah, the snowflake comes down, but it's a little icy. And if it's windy and it's hitting you in the face, it kind of stings. And this is why I call it stinging snow. If the maximum temperature ever exceeds 3 to 4 degrees Celsius, snow will melt completely. So why am I just not giving you one number? Why am I not just saying 3 versus 4? Well, it depends on the size of the flake. A larger flake could survive up to about 4 degrees Celsius. A smaller flake is going to survive about 3 degrees Celsius. All right, so the size of the flake is important. If the Tmax is between 1 and 3 degrees Celsius, this typically results into a partial melt of the snowflake, which will refreeze into sleet, or you can have a mixture of sleet and freezing rain as well, depending on the depth of the warm layer. All right, we're going to talk about that sub-freezing layer later with the sleet, but for now, just remember this. If you're less than 1, still got snow. If you're 1 to 3, you're in that sleet partial melt range. If you're 3 or 4 and above, you're total melt, and you're either rain or freezing rain depending on the surface temperature. If it's above freezing of the surface, it's rain. If it's below freezing of the surface, it's what? It's freezing rain. How thick is that melting layer? All right, so again, we got these, zones, right? I just showed you 1 and less, 1 to 3, 3 to 4 and above, all right? Now we're going to do this with feet as well. If the melting layer aloft is between 1,500 and 4,500 feet, this can support sleet or depends also freezing rain as well. So that's that partial melt zone, that 1,500 to 4,500 feet. If the Tmax is greater than 4 degrees Celsius, which we talked about, especially with the melting layer thicker than 1,000 feet, this will likely result in total melt. Plus, think about it. If you're getting to 4 degrees Celsius, you're almost guaranteed that your melting layer is going to be over 1,000 feet anyway. It kind of makes sense, right? If the melting layer is thicker than 4,500 feet, then total melting will occur regardless of the Tmax, okay? Now, got to be a little careful with that. Going back to what I said. I use about 0.5 on this one, all right? In general, if your melting layer is above 4,500 feet, total melt. And if you have total melt, you have no ice crystal. And what total melt means is no snow, no sleet. It's either rain or freezing rain, depending on the surface temperature. But what if you're 0.1 degrees Celsius for 4,500 feet? Well, then you better be darn sure that the model's correct. And regardless, what will happen as the snowflake falls, it will actually start to melt a little bit. And what I've found is when it's really close to 0, it usually stays at 0 because the melting is occurring and is causing cooling. But when you get about a half degree Celsius or above for 4,500 feet, it's total melt, all right? So below 1,500 feet, we're still in that snow range, just like below 1 degree Celsius. If we're between 1 and 3 degrees Celsius or 1,500 and 4,500 feet, we're in that partial melt zone. And if we're above 3 to 4 degrees Celsius, for sure, if we're ever above 4 degrees Celsius, total melt, or if we ever have a melting layer greater than a half degree Celsius for 4,500 feet, total melt. All right, we're going to practice with this as well, okay? All right, so anytime you do this, this is what I want you to draw, okay? This is these zones we were talking about, all right? Less than 1, snow, less than 1,500, snow. Now, if it's 0.7, it's still snow, but it'll be that stinging snow, all right? Same thing with this. Between 1 and 3 and 4, between 1,500 and 4,500 feet, this is that partial melt area, right? And it'll depend on how cold it gets below, which we'll talk about more a little bit later. If it's ever above 4 degrees, total melt. If it's between 3 and 4, it gets a little tricky, but I'll show you some different examples, and we'll break this down where we can help you understand that a little bit more. And if it's ever above 4,500 feet, total melt. All right, so if your temperature is ever above 4 degrees Celsius, total melt. If your melting layer is ever thicker than 4,500 feet or greater than a half degree Celsius, total melt. All right, if you're in this middle zone, it's going to depend on how cold it is below. And you just got to use intuition, right? So let's say you were at 3.9 degrees Celsius for 4,400 feet. Okay, I guess technically you're still in that zone, but when both of them are near the extreme, I'm going with total melt. Whereas if it was 3 degrees Celsius for 1,500 feet, well, because one is over here and one is over here, I'm probably going to stick with the partial melt. Or the opposite. Let's say, it was 1.5 for 4,400 feet. Same thing. One's on the low end, one's on the high end, so I'd probably stick with partial melt. We're about to practice with this. All right, so let's go through a few scenarios here. All right, so if your Tmax is 4.2 degrees Celsius, stop. You don't even really need to look at this. Yeah, you do want to make sure it's over 1,000 feet, but almost always if it's 4 degrees Celsius, it's going to be over 1,000 feet anyway. If you're over 4 degrees Celsius, it's over. The ice crystal's gone. Total melt, all right? And if you have a total melt, no snow, no sleet, it's strictly freezing rain or rain depending on the surface temperature, all right? Tmax of 0.7 for 6,000 feet. All right, we're over 4,500 feet. Now, if it was 0.1, okay, that's getting in a tricky zone, and I'd probably stick with it not being a total melt. But because it's over a half degree over 4,500 feet, this is total melt as well. So over 4, total melt. Over 4,500 feet, total melt. But what if it's only 0.7 for 500 feet? This is that stinging snow. It's less than 1 degree Celsius, and it's less than 1,500 feet. Stinging snow. All right, it's not going to feel the best. It hits you in the face when it's windy, but it's still snow. All right, 1.5 to 2,500 feet. Now we're in that partial melt zone, right? And I'm going to teach you this, but as long as this gets about minus 4 degrees Celsius below, we can have sleet. So this is that partial melt zone. All right, we have a partially melted snowflake, and if it's cold enough below, we could get sleet in this scenario here. What about this one? 3.3 for 4,000 feet. Well, we're near the top. Technically we're not to 4, but if it was a smaller flake, it would be a total melt. And technically we're not at 4,500 feet. But when we're both at the end there, when we're both at the extreme end, I would say I would lean much more on this as a total melt. Okay? But what about this one? This one I would say partial melt, because even though we're at the end on this one, we're more on the lower end on the other scale, right? So hopefully you can see that. If you're on the extreme end on both, I would almost always go with total melt, all right? If you're on the extreme end on one, but more on the lower end on the other, then I'm going to go with partial melt. 2 degrees Celsius for 2,000 feet, that's in that partial melt zone. So if it's cold enough below, we're going to get sleet. And I know I've said this a few times, but we're going to talk about that. All right, so hopefully that helps you. Now, keep in mind, you can't become an expert on this stuff just watching one lecture, all right? You're going to have to practice a lot. Now, I'm going to give you some practice files, and, I'm going to keep the quiz as basic as I can on this just to make sure that you understand the basic principles and that you went through the lecture. But to get good at this, it takes years and years and years and years of practice, a long time, all right? But I'm at least teaching you the baselines. I'm at least teaching you the overall ideas behind it, that you have a good starting point, and that you should be able to do pretty well, okay? So again, anytime you do this, start with this: 1 degree Celsius to 3 to 4 degrees Celsius, 1,500 feet to 4,500 feet. Always draw this out, okay? All right, so let's break this down in even more detail, all right? The location of the melting layer is important. If the freezing level is lower than 900 feet above the surface, precipitation will most likely be snow at the surface. If the freezing level is higher than 1,200 feet, possibly as high as 1,500 feet, again, it depends on the size of the flake, precipitation will most likely be rain at the surface. Melting depends on the size of the snowflake and the temp of the surface, all right? So no two snowflakes are the same. They're not always going to be the same size. So in this scenario, this is with a melting layer at the surface. What we were talking about before is the melting layer aloft. Now we're focused on the melting layer at the surface, okay? And there's a difference between the two. So you might ask yourself, wait a minute, why is this different than what you just told me? Why is it that a surface-based melting layer of 1,500 feet results in rain, but an elevated melting layer of 3,000 feet may result in sleet? This is where human element comes in versus the physics side of it, okay? So, aloft is that snowflake falls into that partially or into that melt zone, that partially melts. There's still an ice nuclei within the supercooled water, right? But you're not going to see that. Like as a human, like for example, if the melting layer was 1,500 feet above the surface, right? Or let's just say 1,000 feet, and you still had a little ice nuclei when that super cold water hit the ground, right? You're not going to see the ice nuclei, right? It's just going to look like rain or freezing rain depending on the surface temperature, right? So again, what's going on aloft, there's still an ice nuclei present, and when it falls through that sub-freezing layer, it can refreeze into sleet. But for you, you can't see that ice nuclei, right? So the baseline with a surface-based melting layer that we're going to use in this class, a good, standard level is 1,000 feet. Okay, and we're going to use something on BuffKit on the indices called wet bulb zero height. Now, why are we using wet bulb zero height? Because precipitation is occurring. And this goes back to intro to meteorology, all right? We're not just looking at the freezing level. Because of precipitation, we're looking at the wet bulb zero height, okay? So if the wet bulb zero height is above 1,000 feet, it's a cold rain, okay? If it's below 1,000 feet, it's a wet snow, okay? So again, if it's above 1,000 feet and, that cold rain is coming down, yeah, there's probably an ice nuclei inside the rain, or inside the, what was super cool droplets, but you can't see it, right? So to you, it just looks like rain. Now, the surface is above freezing, so I guess I said before you could get freezing rain. You can in this. It's only rain, all right, because you're above freezing at the surface, all right? So we'll break this down in more detail, but remember, there's a difference between the melting layer aloft and the melting layer at the surface. If the melting layer is aloft, you can go through the gambit. You can go from snow to sleet to freezing rain or rain. If the melting layer is at the surface, it's either a cold rain or it's wet snow. There's no in between, all right? Surface, wet snow or cold rain. Aloft, you can get the whole gambit of the whole cycle, okay? Hopefully that makes sense. If for some reason something doesn't make sense, you can always email me. I'm always here to help. One thing that I highly recommend, do not wait to the last minute on this, all right? Look, I'm going to teach you a lot of cool stuff and a lot of different things. I'm going to try to teach you as much as I can. For some people, this will be really easy, especially if you've lived in winter weather areas. If you haven't lived in winter weather areas, this might be more challenging, all right? So if you need help, you can always contact me. I mean, I basically answer emails Monday through Sunday when I can, so I always help you the best I can. But understand there's a difference between aloft and at the surface, all right? All right, so now we got this melting layer aloft, all right? But we need to know how cold it is below that melting layer. And this is what ties into sleet, okay? So when you have a partially melted snowflake between 1 and 3 and 1,500 and 4,500 feet, these snowflakes will refreeze much more readily, resulting in sleet. And there's this weird sugar sand snow stuff that I'm going to talk about later, but let's just focus on sleet right now. And, let's just keep this in when you think of weather in general, I try really hard to make it as simple as I can, but in reality, is it as simple as most people make it out to be? No, it's not, right? Because the atmosphere is incredibly complex, and it goes back to what I was saying early on in this class. It's really a miracle we do as well as we do, all right? So I'm trying to keep this as simple as I can, but keep in mind, there's a lot more complexities to this, all right? But we're going to just try to break this down in a simple way that you can visualize it, all right? So with sleet, when you have this partially melted snowflake, if your sub-freezing layer below the melting layer is, right? So it's below freezing, you have a melting layer, and then below that melting layer, the sub-freezing layer below it that's below freezing, if it gets colder than -5 degrees Celsius, sleet will form, all right? What I've found over the years is -4 is pretty safe, okay? So if you have a partially melted snowflake and it falls through that, melting layer, but it doesn't lose, the ice crystal's still there, it's partially melted. As it leaves that melting layer, now enters the sub-freezing layer. If it gets to between -4 and -5, you're going to get sleet. If you're between -2.5 and about -4, you can have a mix of sleet and freezing rain, okay? So sometimes it's all sleet. Sometimes it's a mix of sleet and freezing rain. But what if you don't get colder than -2.5? If you don't get colder than -2.5 and it's still below freezing the surface, then it would be freezing rain, okay? So partially melted snowflake. If it gets to -4 to -5, we'll just use -4 as a safe bet because I found that to work well. Sleet will form and it'll be all sleet. If you had a partially melted snowflake and it fell in an area where it was more like -3, -3.5, you would have a mix of sleet and freezing rain. And if it fell through a layer where it was only like -1.5 or -2, then it'd be all freezing rain. Okay, so hopefully that makes sense. This is with sleet. All right, so this is this weird thing that happens sometimes. And it's not very common, especially in the lower 48. You really probably never see it in a place like Mississippi or the deep south. Could you see it up north? Sure, all right? But I told you that sleet is not, super cold water that freezes or raindrops that freezes, right? What is it? It's a partially melted snowflake that refreezes before it hits the ground. But there's this weird scenario once in a while where if it's colder than -8 in that sub-freezing layer. So let's say you had a total melt. You have no ice crystal, right? Typically, if you have a total melt, what's your choices? It's either rain or freezing rain, depending on the surface temp. But in this weird scenario, you can get cold enough where actually those raindrops will freeze. Don't really worry too much about this. I'm not going to test you on this or anything like this. I've seen this once before. I saw this once in DC. It was a nor'easter situation where it was you had a warm nose at about 700 millibars. You had a total melt, but it was really cold below it. And it almost looked like this sugary sand sleet. I don't even know how to describe it. It was literally like if you took a bag of sugar or took a bag of sugar or a bag of sand and just put your hand through it. That's kind of how it felt like. I mean, I think I have some videos somewhere. Maybe I could find it and I could show you guys what it looked like. But it was really cool. It didn't look like a normal sleet pellet. It almost looked like tiny, fine grains of snow or sand. All right. I'm not going to test you on this, but I just want you to know that this is there. And it goes back to what I was talking about. There's a lot more complexities to this, right? We're just trying to keep this simple, though. All right. So a word about freezing rain or drizzle. All right. It occurs under two general scenarios: a shower layer of cold air undercups a warm air mass, or you have warm air vex over a cold air mass. All right. There's multiple ways you can get it. Another way you can get it is if you do not have moisture in the snow growth region. All right, and we'll talk about that in more detail here. Freezing drizzle can occur with a sounding that is entirely below freezing. The droplets remain super cool due to the lack of ice crystal nuclei to freeze on. So, let's say the coldest your sounding got to was -5, all right? You're not cold enough to make ice crystals. So you're not making snow or you're not making sleet. If you're not -10 and you're not making ice crystals, there's no snow, there's no sleet. So it comes down to either freezing rain or rain depending on the surface temp. So if we only get to -5 degrees in the cloud, we can't make ice crystals. So at that point, it's either, like I said, rain or freezing rain depending on the surface. But why am I focused on drizzle? Why am I saying freezing drizzle? Well, because if your cloud only gets to -5, you probably have a really shallow cloud. And most of the time when you don't have moisture in the snow growth region and you're not producing snow, you have a really shallow cloud. And to be more exact, it would be freezing drizzle or drizzle, depending on the surface temp, because it's a thin cloud with not a whole lot of moisture in it, okay? And you may think, oh, drizzle, not that big of a deal. Look, even freezing drizzle for a few hours can cause incredible problems, all right? And even if you can't see it, they call it black ice, it can still be really, really, really dangerous because people don't see it, they slam on their brakes, they lose control of their car, and you have a lot of car wrecks, all right? So freezing drizzle and rain is no joke, it's serious business. This was an example where the Weather Service in Grand Rapids saw this, right? So the freezing drizzle threat late tonight into Friday morning looks pretty good. The deep moisture is lost very abruptly, all right? So the moisture producing the snowflakes is lost. And after 0Z from west to east, and that makes sense, the system is moving through and the dry air is coming from the west to east, at which time the DGZ, dendritic growth zone, that is your snow growth region, all right, will no longer be saturated, all right? So if it's not saturated at -10 and you're not making your dendritic crystals, what's happening? There's no ice that will be present, and at that point it's either drizzle or freezing drizzle, depending on your surface temperature, all right? And they saw this, and they were on top of it and had a really good forecast. This is something I see people overlook. They think it's colder than 0 degrees Celsius, so they're going with snow, but if there's no moisture at -10, you're not making ice crystals, you're not getting snow. All right, this is, I won't say a pet peeve or anything like that, but it's something I see a lot of people do, especially here in the South. When it gets to 32, you'll see people start panicking, like freezing rain, freezing rain. Well, yes, if it's 32 or below, it's freezing rain or freezing drizzle. That is true. But what is your ground temp, all right? If we've been in the 60s for the last 2 weeks, are we really that worried when it gets to 32? No, because even though we are having freezing rain, the ground is too warm to cause big problems. But where will you have problems? Even at 32 in trees and bridges and overpasses, you would, because the air is flowing through it. You're getting evaporational cooling, and you'll actually get ice starting to accumulate on either the power lines or trees or things like that. But in general, to get damaging accumulations of ice, so we're talking the ice skating rink, no one can go anywhere, you need to be about -2 degrees Celsius or colder at the surface, all right? If you start getting to, 28 degrees or so or colder, 28, 27, it's over, all right? You're going to turn into an ice skating rink. But be careful. I see people a lot of times, the second it hits 32, they start talking gloom and doom and like, it's going to be the worst ice event ever. Well, the ground's too warm. But once we start getting to -2 degrees or colder, now you got some big problems, okay? Another thing to keep in mind is what happens when you do have freezing rain. The temperature will typically jump a couple degrees. Why? Because as it freezes, it's doing what? It's releasing latent heat. That's why major ice storms typically need some sort of northerly component to the wind to reinforce the Arctic air. Otherwise, latent heat release and advection will cause the temperature to rise above 0 degrees Celsius or hover right at that 0 degree line where it won't be that bad except for, overpasses and bridges and trees maybe, all right? So maybe, I don't know, Minnesota, maybe if it's been, sub-freezing, -20, -30, -40 for the last 2 weeks, and you're right at 32, okay, now you may have problems. But typically most places, especially down here in the South, when our ground temps are usually above freezing anyway, we really need to be at the -2 degrees Celsius, and we really need that northerly component of the wind to keep reinforcing that cold air, because as that water freezes, it releases latent heat, and you have to have something to offset that. The ground temperatures are very important when temperatures are close to freezing. What has the weather been like recently? All right, this is where following the weather every single day is important. And if you Google, soil temps or things like that, you can find a lot of websites that will give you the soil temps at like 2 inches, 5 inches, 10 inches. Different sites will give you different things on that, but that's really important. Always look at the ground temp when you're expecting winter weather, all right? That's really important. And always also remember the bridges and overpasses freezes first. Even if we're right at 32 degrees and the ground is warm and you're not looking at a devastating event, you can still have problems on bridges and overpasses. And especially here in the South, unfortunately, people aren't as used to driving on it. And what's people's first reaction when they get on ice and they start to slide? Hitting their brakes. And that's the worst thing you can do. You don't want to hit your brakes in that situation. All right, so a couple thought questions, and then we'll end with a couple little practice quiz questions. Can sleet occur with a surface temperature above freezing? Yes, definitely, right? Snow can occur with a surface temperature above freezing, right? When that wet bulb zero is 1,000 feet or below, you can still get wet snow. But I've seen sleet in the mid 40s. In general, sleet can survive about double the melting layer, okay? So if a snowflake with a surface melting layer, we're not talking a lot, surface melting layer, if it's 1,000 feet or below, you still have wet snow. With sleet, you can double that. You can probably survive about 2,000 feet or maybe even a little bit more, all right? It depends on the circumstance, depends on how cold it is aloft. There's a lot of other factors, but I would say about 2,000 feet, about double the melting layer sleet can survive. All right, so a couple quiz questions. What is the precipitation sequence if the sounding is entirely below freezing, then warm air arrives aloft first and then works its way down the surface? So aloft, right? That's the key word, aloft. So if warm air is aloft, that's how we can go through the gamut, all right? Now, if it's -10, you're producing snow, you can go from snow to sleet, as long as it's -4 to -5 below, to freezing rain to rain, all right? So aloft, you can go through the whole cycle. But what if we switch this? What is the precipitation sequence if the entire sounding is below freezing and then the surface goes above freezing? The surface-based melting layer continues to warm and gets thicker. So this is that wet snow to cold rain, all right? So as that Melting layer is expanding and we get to 1,000 feet, we're still good. We're still got wet snow. But if it's above 1,000 feet, we start getting above 1,000 feet. Now, again, it depends on the size of the flake. They can maybe survive up to 1,500 feet. But 1,000 feet is a good baseline. It starts getting above 1,000 feet. Now we're in the cold rain, all right? So aloft versus the surface, all right? There's a difference. All right, so now it's time to apply all this, all right? Look, I'm trying to teach you as much as I can in the best way I know how to do it and really give you all the tips that I know, okay? But to get good at this, you got to practice a lot. You got to have experience. You got to look at real-time events. If you're going to rely on this one lecture and my, 10, 15, 20 practice files I give you to become an expert, that's impossible. It'll give you the baseline to have a good starting point, and they'll help you grow as a forecaster and get better, but you got to put the time and effort into this, all right? The best forecasters are the ones that do it the most and have the most experience, all right? But still, I'm going to go through several practice scenarios with you. So we're going to kind of put a pause on Lecture 8 here, and then we'll return with Lecture 8 going through several practice scenarios.